Greetings and welcome to Distillate. Let's attempt another tutorial of solving differential equations. And this time we are going to solve multiple differential equations. Um, and for that, the system that I have considered over here is tanks connected in a series. So the system basically looks something like this. We have a given tank with the cross-sectional area over here equal to A, and there's an incoming fluid, and the bottom of the tank is connected to another pipe from where the fluid is going out, right? And the area of this pipe over here is, let's say, small a, right? If the height of this particular tank is, say, h naught, the height of fluid in this particular tank, then we could use Bernoulli's theorem over here. Since the pressure here and here is going to be the same, therefore we can very easily say that the velocity of the fluid coming out of here is going to be square root of 2g h naught, right? And therefore the flow rate is going to be a square root of 2g h naught times a, right? Now the system that we are considering has tanks like these connected in series. So we'll draw it below. So we have a tank like this with fluid at a height h naught. There is something coming in, something, and this area is A. There's something going out. We have already evaluated what that Q naught is. And then this becomes the inlet flow rate to another tank. For simplicity, right now I would consider maybe the same cross-sectional area of the pipe that is connecting, the outlet pipe as well as the cross-sectional area of the tank. We'll just consider the same, but we could further extend this model for different cross-sectional areas as well. But let's just, for simplicity right now, since we are just beginning our journey of differential equations, let's just consider the same cross-sectional area. So this is A once again. This is once again small a. If this height is h1, so I could very easily say that q1 is a times square root of 2g h1, and so on. There could be multiple, let's say, n such tanks connected in series. Therefore, for the last tank, since I've started my numbering with 0, so therefore the last tank will have height hn minus 1, and the inlet flow rate to this is going to be qn minus 2, and that is going to be a square root of 2gh n minus 2, and the outlet flow rate from this tank is going to be qn minus 1, which is a times square root of 2gh n minus 1, right? So that's going to be the scenario over here, right? The only thing that we need to fix right now is the inlet flow rate. So that's something that we can keep in our control, and based on that, rest everything would change accordingly, right? So this is the system. Now let's start formulating the set of ordinary differential equations to solve this problem. So let's just do a volume balance. So considering incompressibility, let's just balance the volumes. So we'll say that for the tank 0 over here, the mass balance or the volume balance in this case becomes equal to whatever is coming in minus whatever is going out is equal to whatever stays, which is dv by dt. And since the cross-sectional area is constant, that just becomes a dh naught over dt. And this further can be written as dh naught by dt equals to q in over the cross-sectional area. Let's just say that this is equal to some parameter with the same units as velocity. So let's call it v in, although that's not the same as velocity, but let's just say that's some parameter v in over here. And then minus q naught is known to be a times square root of 2gh naught, and there's an a divided by a capital A divided by this. So this becomes v in minus, let's just name the parameter a by a as the ratio of the cross-sectional areas of the pipe, the outlet pipe, to that of the tank. So let's call this r, right? So r times square root of 2gh naught. That is going to be the ordinary differential equation governing my first the tank 0 over here. And remaining tanks, let's just try to balance for this thing. So the balance for this thing just becomes dh1 by dt equals to whatever is coming in. So that is a by capital A square root of 2gh naught, which is just r times square root of 2gh naught minus r times whatever is going out. So r times square root of 2gh1, right? That becomes the governing equation for the first tank over here. And a general ith tank except for I equals to 0. So we could write dhi by dt is equal to r times square root 2g, that we could take common, times square root of hi minus 1 minus square root of hi. And here we have I equals to 1, 2, and so on till n minus 1, right? So that is what we have. And for I equals to 0, we have this v in minus r root 2g times square root of h naught, right? So this is the set of ordinary differential equations that we have to solve. And let's say we have the initial condition. So at time t equals to 0, let's say, just for simplicity, we could just say that every tank has the same height h to the power 0. I mean h superscript 0. Sorry for the notation. So maybe let's just say that at t equals to 0, we have h naught equals to h1 equals to h2 and so on equals to h n minus 1 is equal to h superscript 0, right? That's the initial condition over here. And once again, you could add more complexity to the problem. You could have various different initial conditions. So I would imagine another useful initial condition would be that everything is empty in the beginning before it starts to flow, and so on and so forth, right? So we could do all of this together, right? Now, the interesting thing about this problem is that it has multiple ordinary differential equations and all of them are coupled, right? So if we go on to solve this a set of ordinary differential equations using, first of all, analytically, it's going to be very challenging to solve, right? And if we go on to solve this set of ODEs numerically using implicit methods, then again, it's going to be very challenging because you'll have to use non-linear algebraic equation solvers. So that could add to the complexity of the problem. But we'll be using, for this problem, we'll be using the Euler's explicit method once again. So that would definitely make the problem a lot simpler, right? So now that we've been able to set up the problem very well, let's go ahead and try to solve this using Python, right? So once again, I have got my libraries imported. I have got my parameters, which is the like not the velocity, but okay, the flow rate divided by area at the inlet. I've got the ratio 0.2, like the ratio of the pipe area over the cross-sectional area of the tank. I've got my acceleration due to gravity, and we saw the square root of 2g occurring many times. So we've considered that as an additional constant. In general, whenever we are coding, we try to evaluate as many constants as we can outside the loops so that we don't have much trouble with the calculations inside, right? Just like the last tutorial, we next move on to initialization and definitely initial conditions. So we have number of tanks. We've taken it to be 10 right now. This is the initial height that I have given at the moment. And then we have the H array, similar to the velocity arrays that we had for multiple particles in the previous tutorial. We could have the height arrays for multiple tanks, right? So once again, the outside is going to be the main list. H is going to be a list, but each element in the list is going to be a numpy array. And the numpy array would comprise of the heights of each of the tanks at different times, right? That's what each element in the numpy array would represent, right? So since this is going to be the initial condition, let's just write down. So as we wrote it for the velocity initial condition in the previous tutorial, let's write it for this one as well. So it's np dot ones, and this time there are going to be as many tanks as the number of as many heights as the number of tanks. So therefore np dot ones n, so that would give me a numpy array of n ones, right? And I'll multiply that by the initial height h naught. Once again, this initial condition could change. This could be different. Each tank could have a different initial height and so on and so forth, depending on the problem that you're dealing with. This is the simplest version because we are just starting, but you could attempt more complex versions of this particular problem, right? Once again, we have the time array, and we have the final time up to which we are trying to simulate this, and the time step. Then we have the loop for our Euler's explicit method, and inside the loop, we are going to do our calculations once again, right? Now there are a few things that I want to cover before I actually go ahead and solve this problem. So the first thing that I want to cover is how to append a value to a numpy array. So let's say if you have, let me just import numpy in my command window over here. So import numpy as np. And then if I, let's say I make an array, r equals to np dot array 2, 3, right? So now we have the numpy array 2, 3, right? Now, in a general list, what you would do is you would just say r dot append, let's say 5, but that would not be right for a NumPy array. That's not the correct syntax for the NumPy array. So what you do for appending something in a NumPy array, it's just slightly different. So you say np dot append, and inside you write the name of the array. So the array was R. So you're trying to append something to R. So the name of the array would be written over here. And after that, the value that you want to append. So let's say 2. And this would lead to an array that has been, that's R appended with the value 2. Now, if we see the original array R, it won't really change. So if you want to change the original array R, you would actually have to write it as this: R equals to np dot append R comma 2. So now this would append, let's not append 2, let's append 1, just so that there's a different element, right? So what this would do is this would append the element 1 to the array R, and after that it would store the new array that it has created, just like over here. It would store the new array in the variable R. So now the R would be replaced, instead of the array 2 comma 3, it would store 2 comma 3 comma 1. So now that's the new array over here. So this is how you append a value to a NumPy array. So make sure you remember that, because we'll be using all of that quite a lot, right? So this is a difference between appending an array to appending an element to a list versus appending an element to a NumPy array, right? So once we have this thing sorted, let's now move on to the evaluation. So one thing that we see very clearly over here is that except for the first element over here, every other RHS has a particular form, right? There's some form that is associated with each RHS, which is hi minus 1 minus hi, and the square root of hi minus 1, square root of hi, right? So what we could do is we could maybe say RH equals to np dot array, and over here we could write the RHS for the first element, which is the RHS for H naught. So that's just Vi minus R. I'll write it: Vi minus R times square root of G, which is the constant C1, square root of 2G, times the square root of H naught. So that's going to be times np dot sqrt. And remember, this is the RHS of the Euler's explicit method. So therefore, this should involve the element that we are trying to, the height of the tank 0 in the previous iteration. So that's just going to be H minus 1, and that gives me this array over here, and I'm trying to access the 0th element of this array. So that's how you write the RHS for the first differential equation, right? And for all the other differential equations, we'll just say RH equals to NP. Let me just check one more thing before I actually go ahead. So what if I append an array to an array? So, okay, this is what happens. So we could do that. So np dot array, and now we are going to append the entire, sorry, 1 second, np dot append, and now we are going to append all of the other RHS to this particular array. So RH comma, and now we'll make the numpy array for all the other RHS. So actually that's not even necessary. The numpy.array is not necessary. So now all the other RHS can be written as r times square root of 2g, which is just r times c1 times. Now, if you are trying to write the RHS for the ith element, that's going to be square root of hi minus 1 at the previous iteration minus square root of hi at the previous iteration. So, and this I over here goes from 1 to n minus 1. So therefore, I minus 1 is going to go from 0 to n minus 2, while I is going to go from 1 to n minus 1, right? So this is just n p dot square root h minus 1. That's the previous the height array at the previous iteration, and this is going to go from 0 to n minus 2, right? Minus np dot square root h minus 1, and this is going to go from 1 to n minus 1, right? So that's the array over here, and after that let's just check the parentheses properly and we are done, right? That's the RHS computed for all the differential equations, right? So now this is going to have n elements. This particular RHS is going to have n elements, right? And now it's just the Euler's explicit method. So t dot append t minus 1 plus dt, and we'll have h dot append h minus 1 plus dt times the RHS. RHS was evaluated at the previous iteration. That is, it was evaluated at h minus 1, right? So that is done, and that's it. We have solved this system of differential equations. And once again, for plotting, we would start by saying we would start by going on for all the plans. So for I in range n, plt dot plot, and as I discussed in the previous tutorial as well, if you are trying to access, in the previous tutorial we were trying to access the velocity for each particle, which was the columns of the matrix. Similarly, over here we are trying to access the heights of each tank. Therefore, it's going to be the columns again. So first let's make the height as a numpy array, so that accessing columns becomes a lot easier. And now we are going to just access all the columns. So it's going to be h all rows, comma, the ith column, right? So that's going to be the case. And once again, label equals to I, which is the tank. So you could maybe store it as a string. So this is the tank number, right? And that's it. plt.legend, plt.show. It would also help to have x and y labels. So plt.x label, that's going to be time. plt.y label, that's going to be height, right? And that's it. So if we solve this problem, there seems to be an issue. Okay, sorry. This goes from 0 to n minus 1, and this goes from 1 to n, because n minus 1 is not accessible. Similarly, n is not accessible over here. So yeah, and these are the values that we've got over here. This is the plot. So as you see, the first tank, it just goes this way. The second tank goes this way. And as we go to the ninth tank, it responds after a certain time. And then it goes on and eventually reaches the steady state height. By the way, the steady state height for all of them is going to be the same, which is so from all the other equations for all i's except for I equals to 0, we get that at steady state hi minus 1 is going to be equal to hi, which just suggests that all the heights are going to be the same, and the value of the height is set by the first equation for h naught over here, which is just v in upon r times square root of 2g. So let's just evaluate the steady state height over here. So v in upon r times square root of 2g is 1.1288, and let's see what is the final height of, let's say, any of them. Let's say the fifth column over here. So that's 1.27. I think I might have. Okay, we'll have to square that because v in upon r times square root of 2g is going to be the square root of h naught. So that therefore the square of this thing is going to be the steady state height. Yeah, 1.2742. So that's the steady state height that we've achieved, and all of them are going to have the same steady state height, right? So that's an interesting observation that we have seen over here. And we could just go on for multiple tanks. Let's go for 100 tanks and see what happens. This is going to take some time, and let's just not display the legend maybe because it's going to be hard to see. But you see that as you're going towards the right over here, you see the tanks are slowly starting to fill. So for example, the last tank has probably started to increase its height at some time around 60 seconds, right? So as you increase more and more tanks, the time at which the last tank begins to react sort of changes drastically, right? So that's something that is good to know from this particular problem over here. Now, one thing that you might also be interested in understanding is what would happen if I suddenly change the sum of the parameter, right? So let's say, what if I suddenly increase the inlet velocity? How would all the other tanks react to it? So let's maybe try to see what happens. So what I'm doing is that when I am reaching, let's say, 50 time units, so for all times greater than 50, I'll say that my inlet velocity would change to 2, let's say. So I could say if t minus 1 is greater than 50, let's say, I would change my vi to 2. And then what would happen? Now, in order to see what exactly is going to happen, we would really want to track v as well. So maybe let's just make a v array v, and that becomes vi over here. And every time I append vi to my v array, right? In every iteration, I append my vi to my v array. And after that, I'll just plot T versus V plot and see what happens, right? So let's see how this actually turns out. So you see at 50, the velocity has changed. This is a step change in the the inlet velocity. And because of that, you see that at 50 seconds, this has also changed drastically, right? And once again, we see that the tanks had reached their steady state heights. And then once again, the first tank immediately, as soon as we see the change in the inlet velocity, the height immediately increased, right? However, it took some time for this change to be reflected in the last tank, right? So this particular effect of some change in the parameter in the initial tank itself, it would take some time to propagate over the rest few tanks. This kind of an analysis is very well done using process dynamics and control. So we chemical engineers study about that in detail by developing transfer functions for various systems. So over here, let's say if we want to assess how the height of the last tank would change depending on the change in the initial flow rate, we would actually develop what is called as a transfer function between the which relates the height of the last tank to the inlet flow rate, right? So we could do all of those things. We could solve these differential equations, but the overall objective is to study how exactly does my system change over time. And you could evaluate various quantities such as the time constants and everything to quantify this change, right? So that's something that you can do. There are multiple other things that you can do. You could maybe vary a velocity for, you could see what happens with a pulse input. So let's say if I say that if my t minus 1 is greater than 50 and let's say less than 50.1, let's say we are keeping this change very short, right? And then we'll change vi to 2, and otherwise we'll change it, we'll keep the vi as 1. So now let's see what would happen. Let me just erase all of this. And now if we see, there's a slight change that was observed over here, which was probably reflected later on, but we don't really see all of that too much. But let's say if we would drastically change it to 10, let's say, this is a pulse input, right? So now you see a much better change over here. So you could do a lot of such cool things with these kinds of solvers that we are developing. So this code has been provided in the Google Drive link. So please play around with it, try to change the nature of the inputs, maybe make a linear input or sort of thing, and just play around with this and see how this turns out, and implement new things, implement other complexities in the system. And it's just fun to operate in this with these kinds of systems, right? I would really love to see what happens if we keep it for longer times. So let's say I'm keeping the velocity as 10 for 10 seconds. And in that case, we see a much more interesting behavior. And let's just observe this for a little more time. So we see this very cool sort of a behavior. So yeah, that's pretty interesting, and hopefully you would enjoy this a lot more. So please do play around with this. and hopefully you learned something good out of this tutorial. That would be all for today's tutorial. The last tutorial that I will be working on for ordinary differential equations would be reactions in series, and if possible, I would also like to cover reactions in parallel reactions. So in that case, you get again a coupled set of ordinary differential equations, and it's again interesting to observe the kinetics of such reactions, how the concentration profiles change, and these concentration profiles, this kinetic data is once again very useful for designing reactors. So I would do that. That would be the last tutorial. In case you would want me to discuss problems uh, other than these as well, please do feel free to reach out to me through comment section or the email that I've provided in the description. So hopefully you enjoy Python and keep exploring more and more interesting chemical engineering concepts using Python, and hopefully we'll be able to learn and explore this programming language and apply all of it to our chemical engineering core curriculum. So yeah, thank you.